Okay, good morning, everyone. I'm Guo Towards from Lanzhou, China. My talk will focus on the experimental proof of researches on wobbling bands. Oh, what's the matter? Okay. Wobbling motion in atomic nucleus is in fact complicated. However, its picture is similar to the precession of a gyroscope or a top in normal life. This conception in nuclei was introduced by Bohr and Monson half a century ago. Recently, by taking into account the coupling of the quasi-particle and the triaxial deformed curve, transverse and longitudinal wobbling have been raised by Frondorf and Donald. Experimentally, many such wobbling bands have been reported. From the beginning of this century, a series of wobbling bands were first observed in the 160 Mars region. Recently, several wobbling bands are reported in other regions. In fact, this should be regarded as two groups of wobbling bands, constituting the different deformation, different spin regions, and different interpretations. In this talk, I would rather to focus on the recently reported wobbling bands. The lever structure of a wobbling band is similar to the signature partner band. The key experimental criteria to distinguish it from other explanations are the E2 dominated linking transitions between the wobbling band and the yrast band. Based on the E2 M1 mixing ratios, the reduced electromagnetic branching ratios can be deduced and further compared with calculations. One should also discuss the wobbling frequency to see if it is a transverse or longitudinal wobbling. But before that, the mixing ratios of the linking transitions should be deduced first to see if it can be explained by wobbling. The mixing ratio, or delta, was deduced using two spectroscopy methods: angular distribution and linear polarization. The angular distribution is related to the spins and parities of the initial and final states, and the mixing ratio of different components, such as M1 and E2. Thus, it can be used to deduce the E2 M1 mixing ratio by comparing the estimated curves and the measured results. The curve changes with delta, so there will be some certain value with certain error leading to the agreement between the curves and experimental results. In the work on precession 135, the delta values were deduced using this way. However, Y, can you notice Y, the curve with a small delta here, looks very similar to the other two with much larger delta. In fact, for the M1 E2 transitions with negative delta, first of all, they are symmetrical about 90 degrees. So to be simply fair, I only plot the left half for the small deltas and the right half for large deltas. With the zero delta, namely a pure M1 transition, the curve is relatively flat. When the magnitude of mixing ratio increases, the both ends of the curve decrease from here to here. But after it crosses a point near to delta equal to -1, the curve will raise up again at both ends. Therefore, the curves with a larger delta and a smaller delta can be similar. Then for such an analysis, a proper way is that deducing two solutions on delta first, one larger and another smaller. Then comparing the two curves with the experimental results to see if one solution can be firmly excluded. In fact, we did such a work on the precession 135. Besides the reported curves, we added an extra curve in each figure for comparison. As it is shown, the two curves are quite close. and cannot be distinguished within the reported errors. Therefore, using the experimental results on angular distribution, it is impossible to exclude the other solution. For the linking transitions between the wobbling and the yrast bands, their mixing ratios are deduced to be large, leading to a predominantly electrochromic nature. However, if another smaller solution is adopted, this should be dominated by M1, which means a non-wobbling interpretation. After this work, two following works have been published, which are also performed with gamma sphere. For them, despite the two curves are still similar, it seems the published one can fit the experimental curves better, especially for these two, these in God 187. Can it be a strong support for the reported delta values? In fact, the counts in these figures were not measured directly, but deduced from a gamma-gamma matrix built on a huge number of coincidence events. To deduce the peak area, one should obtain gated spectra first, and then fit the peaks. In this process, one should use a series of parameters, such as the canals to gate, the canals to subtract the background. So therefore, the final counts are in fact affected by the parameters which are artificially selected. If the uncertainty induced by the artificial factors cannot be properly evaluated, it is meaningless to compare the fitting or the chi-squared values. However, for the two works, the errors are extremely small, so that even the reported curves, you see, cannot meet most points within their errors. In fact, for most points, there are no errors. Comparing the two works with the former one, which are all measured by gamma sphere, it is further surprising that the errors that are significantly shrunk in the later two works for transitions with, in fact, similar statistics. In my opinion, it is necessary to explain how to restrict the uncertainty to such an amazing content. Such analysis was also used in another work with Inga, the lanternum 133. Again, the two curves cannot be distinguished within the errors, even though the errors are still questionable. In this article, the angular distribution on another transition, this 789, was reported as a reference. You can see the counts for this 789 is much larger than the three linking transitions. However, for about 30 counts of the four transitions, their relative errors are very similar here. Usually, the statistical error is the major part of the total error. Therefore, generally, the relative error decreased with increasing counts. Of course, there can be some other factors to affect it, but it is still amazing to see so identical relative errors for so many counts. I'm afraid it cannot be attributed to chance. Similar story happens on the deviation between the curves and the experimental points. With the best statistics, the 789 is expected to have the smallest deviations, but in fact, no. Another experimental approach is the linear polarization measurement. For such an analysis, there are some experimental inputs. First of all, the peak areas, which are reported only for the two works, are lanternum 133 and God 183, among all the five works. Besides, there are three parameters: the asymmetry correction A, the polarization sensitivity Q, and spin alignment parameter sigma per I. This should be calibrated or evaluated. However, in all the 5 works, nothing, but only one asymmetry correction for Presidium 135 is mentioned in a PhD thesis. The absence of those essential information makes it difficult to assess the reliability of the reported experimental results. However, we still found some problems. For example, the first wobbling band out of the 160 mass region was supported both by angular distribution and by linear polarization in Presidium 135. We have mentioned that the 2 solutions on delta cannot be distinguished by the angular distribution. Then, what about the linear polarization? In fact, the positive asymmetry was deduced in that work, and it was taken as a proof of the E2 dominated corrector, as written in their paper. However, the positive asymmetry, which has the same signature of polarization, can be achieved by both larger and smaller solutions deduced from the angular distribution. Therefore, the small one, in fact, has not been formally excluded by the 2 measurements, and so far it is not sure if it is a real wobbling band. For another nuclei, lanthanum 133, again, it was reported by both angular distribution and linear polarization. I have shown before that the angular distribution cannot decide which solution should be adopted. Now, from this figure, it seems the larger solution is well supported by the linear polarization. However, the polarization is deduced from the count ratios here, which show a clear zigzag pattern for the 3 transitions. See here 1.27, 1.07, and 1.26 is the ratios are deduced from the figure. But the polarization values are quite similar. It is interesting. So we used this formula. This formula usually is used to obtain polarization from count ratios. But now they are both reported, while the 2 calibrations A and Q, they are not reported. So we plotted the possible AQ to make this equals to a figure. We plot the possible AQ values for each transitions according to this formula and get the 3 lines in this figure. You see, this is for 758, this is for 874, and this the above one is 982. However, you say it is impossible to find 3 reasonable points in this figure. Since the 2 calibrations A and Q, they are both smoothly changed with energies, 3 points can only be found when the lines for 3 transitions located in sequence with their energies. But the line for 874 is much lower than the other 2. In fact, what's that? In fact, it seems proper values can only be adopted for the 874, since the Q value for the other 2 should be too large. Therefore, the result is also questionable. This is a very recent work reported only several months before. For this work, we found the statistics are rather poor for the linear polarization measurement. Then we analyzed the statistical error for the 495 transition and obtained a quite large error for the polarization, larger than 0.6. And you see the reported error is about 0.09. The statistical errors should usually be regarded as the lower limit, and this reported error is significantly underestimated. With the statistical error, the two solutions cannot be distinguished. This is the case for 495. And here, this band, this wobbling assignment is supported by two linking transitions, which are claimed to be E2 dominated. One of them is 495, and the other is 498. But it is even more puzzling. How can the ratios for 498 be deduced? You see, there is another 498 here, just above this one. In fact, according to the known level scheme, no transition can be used to create a clean gated spectrum for the lower one without the contamination from this upper E2 transition. So it's also questionable for this nuclei. And this spring, when I read the article on the God 187, I found it is quite interesting. It is declared to be the first longitudinal wobbling. According to this paper, such a wobbling is achieved when the quasi-particle raise up from the middle of jet shells. However, since the quasi-particle occupies the intruder H9½ orbital, it should be located at the lowest or the second orbital. I don't think they can be regarded as middle jet orbital. Furthermore, as I mentioned before, the experimental results are only deduced from the angular distribution with extremely small errors. Therefore, we perform the experiment to check the carrier of this band. This experiment was performed in the heavy ion research facility in Lanzhou, in our institute. An oxygen 18 beam was used with the beam energy at 108 MeV. Using the natural lutetium target, the proportion of God 187 is about 2/3. This is our detector array consisting of 8 clovers and 16 coaxial germaniums. 8 clovers are all located at 90 degrees, where the germaniums are put in 4 rings. Unfortunately, only 8 anti-Compton shells were equipped during this measurement. The other shells will be installed after a few months. Therefore, we need more statistics. So we employed a DAC based on XRA digitizer, which allows high counting rates. This is the label scheme from our work. This branch in red was reported in the last article on wobbling, which is regarded as a rare signature partner band. And since it is found, the original signature partner should have an alternative explanation, which is the wobbling. However, we found the transitions in the red branch are totally overlapped with 4 transitions in the ground state band and gamma band of the neighboring platinum 188, which here. Due to the contamination, the only proof to prove the existence of the same sequences in God 187 is these 2 linking transitions, 437 and 429. However, they are both absent in the spectra gated by the transitions they feed into. Therefore, the existence of this branch in God 187 cannot be supported in our work. To deduce the ratios for the linking transitions 376 and 462, it is very important to select proper gating energies. In this work, it is very easy for 376 since it is clean. We just use the 7 strongest peaks in the spectrum gated by it. But it is difficult for 462, since there is another 463 above. So we must avoid the combination. And this one is in fact in coincidence with most of the strong transitions. Then we compared the spectra gated by the 462 and 279, which is below the 463 here. Then we found that only the 316 and 400 are proper gating energies, since they exist only in this spectrum, not in this one. However, here is also a 465. To avoid the contamination from this one, we have to use only the left half of the 316 peak, because there is a close transition here with much lower counts. Therefore, finally, we have to combine the information from the two spectra. Note that the 465 is U1 transition, which has larger polarization and larger AD ratio. Therefore, its involvement will increase the two values. So we can still use its upper limits from this spectra to restrict the results. There are the calibrations used in this work. The left one is the asymmetry correction calibrated by standard gamma sources. And the right was reported in a former article where the same type of clover detectors were used. In this experiment, the strongest transitions are generally affected by isomers, so that we cannot deduce useful sensitive curve like that. So we plan to do that in following works. In this work, we used a PADO method for the polarization analysis, which is very similar to the well-known PDCO. In my opinion, the PADO has some advantages. First, more statistics can be used. And second, ADO ratio is independent with the sigma per I parameters of the gating transition. As shown in the figure, it's only affected by the sigma per I parameters of the transition of interest. This sigma per I is usually regarded as identical for other transitions, but for low spin states, it is a better assumption. Say, for example, the deduced sigma per I in Cerium 134, it varies. You see, for the highest, it can reach about 0.6, very high. So for in the low spin region, we must be very carefully for this parameter. Third, using the PADO method, several spectra gated by different transitions can be summed up to further increase the statistics. For the details, I plan to write a paper to introduce this method. Using this method, we deduced the polarization and ADO ratios. Here is the polarization, and this is the ADO ratios. And plotted them in this figure. As mentioned before, it is important to decide the sigma per I parameter, but it is difficult, especially in this work, due to several known isomers, which will make the sigma per I parameter very large. Therefore, we plotted a series of PADO curves with different sigma per I parameters. Then we did not restrict this parameter in the analysis. So our errors should be larger, but more reliable. We also plotted the red points using the reported large mixing ratios in the wobbling paper, which cannot agree with the experimental results with any sigma per I parameter. It is worth noting that the polarization value for 376 has been deduced 30 years before, which is very close to our result. Furthermore, the internal conversion electron has been measured in two former works several decades ago, and the coefficients are in agreement with our small mixing ratios, but disagree with those reported large mixing ratios. Based on the experimental results, we further compare them with the calculations. They are in good agreement when a small gamma deformation is used for calculations. And according to the contributions to the wave functions, the excitation from the yrast to the yrast band is mainly non-collective excitation, which firmly rule out the wobbling character. We also plotted the results from the wobbling paper, which is clearly not in agreement with neither the calculation or other experimental results here. In summary, several problems have been found in the experimental proofs for the recently reported wobbling bands. So great risk is taken if the researchers at this topic continue with the unreliable experimental results. I know many outstanding theoretical efforts have been devoted to this topic, but it would be a great loss and waste if they are based on careless experimental works. While experiments involving angular distribution and random polarization measurements have been performed, ruling out the wobbling nature of the reported one in GOD 187. In fact, not only this one, there are some other reported wobbling bands. They are all questionable. So a series of experimental works should be done to reinvestigate the nature of other reported wobbling bands. And yeah, what's more, standard technical process for each involved facility should be summarized and published to guide the users to avoid further mistakes. Thank you, everyone. Hope tomorrow is better.
We can't hear you, Powell.
Can't hear you.
No. Is somebody speaking? So what's the
Now, can you hear me?
Yes.
Yeah.
Yes.
Can you hear me?
Yes.
We can hear
Okay,
you.
fine. Thank you. I have a question. There are any question to the talk?
Yes.
Yes, please. Martin, next speaker, please.
I don't have question. I have comment. We performed a very similar analysis as you were presenting for 187 gold in-beam data with nearly exactly the same conclusion. We also cannot confirm this wobbling, exactly the slide that you are showing now from independent data taken at Itemba Labs. So maybe we should get into the touch and discuss these things. Thank you.
Yeah. Welcome. Also on this nuclear, the GOD 187.
Yes, exactly.
Oh, it's good news.
Oh, we have exactly the same conclusions.
So Do you find this this
Exactly.
branch?
We made the same conclusion as you were presenting.
Can I have one more question?
Yes, please.
Yeah. So first of all, I think when we are trying to derive the mixing ratio from the polarization asymmetry is not reliable, I think. Because you have to include the, first of all, we are taking assumption of a sigma by j, which may be relevant for the other band, because two band cannot now have the same sigma by j. This is the first comment. Secondly, that the polarization Q sensitivity which you are calculating, it also need a direction input inside. Because it cannot be same for same beam combination. Your different combination, the sensitivity has to be changed.
Yes. Yeah. Yes. They will depend on the reaction.
Yeah. So we have to need to be basically how theory has to be improved a little more also to like these things.
Yeah. That's why in the beginning I want to deduce the sigma per I. But finally, I can't. Then I just leave it free. I compare with every possible sigma per I.
And second, my thing is that because when you're using the angular distribution for getting this delta and getting the polarization ratio, I think they never agree each other.
Well,
yeah, so you have to see how these three independent extraction of mixing has to be concluded together, because there are three independent measurements, and when you're comparing with the conversion coefficient, they have different techniques. So we have to be a little careful when we are comparing them together.
Yeah. You mean this? You mean this part?
No, I mean that when we are comparing the mixing ratio coming from the angular distribution, RDSO value, and polarization measurement, and the conversion coefficient. We can't compare all them in the same footing.
Here?
Yeah. No,
yeah.
Yeah, we need to have because these are dependent upon, apart from the conversion coefficient, all dependent upon some theoretical inputs.
Yeah, in fact, this one is more useful without the calculated results.
Okay, I think that.
Yeah, I have one question, one comment maybe. Can I?
Yes, please. If it's short, so please comment. It's more than well.
So actually, what is a nice talk song, but I have few comments about the angular distribution. Two possibilities of this delta mixing. One is less, and one is in the higher side, right? So to be conclusive about this delta mixing, you have to incorporate the polarization as well. So the work in the wobbling motions, they include this polarization and try to come to a conclusion, right? So if you put the DCO ratio and the angular distribution, whatever angular distribution and the polarization in two axes, and then you put your experimental point in that particular domain with different delta, then you come to a control plot that you have shown here, P versus RAC, right? In the slide it is showing. So the same thing, this point, when it is coming to a conclusive thing, then this point should be conclusive. And for those cases in other wobbling motion, they must be come to this kind of plot, and they conclude it from that particular plot with the polarization data as well as the angular distribution or DC ratio data. It is not that they have conclusively said from angular distribution only. So they have the data for polarization as well as DC ratio. So they must have come, you have already shown this 183 gold that they have come with the linear polarization as well as RDC ratio. And they have in the contour plot, they have a definite point in that particular contour plot. So from there, they can conclude it as a higher data mixing. So I don't know if only angular distribution is considered, then it is something like both of the possibility can be happening. But if we include this polarization, then I think there is no confusion about this delta mixing.
In fact, I think the angular distribution is available for some delta values, especially for some very large or very small delta values. The difference is apparent enough. But of course, the errors should be very carefully treated. You see, for this, if it's minus 5, the behavior of this curve is very different with this one. But in contrary, if it's only minus 1.5, it's very difficult like that. Like for those curves, they are too similar. But here it's possible.
Okay, I think that we can. We have to break for and move this discussion, very detailed discussion, into the chat or other forms of internet communication. Let's thanks again to the speaker.